Well, I'm a little out of my depth here. I knew coming in, I knew coming in that I didn't know anything about philosophy of mathematics or about the history of mathematics, and I knew that I don't really have too much to say about depth in mathematics either. And then now this morning I discovered that there's whole swaths of mathematics that I don't even know about. So I thought a kind of role I might play is just to give a few examples of some things in mathematics and my reaction to them. I have a hard time distinguishing between what's deep and what I like. So I just wanted to give you a sort of impressions about a couple of things. And I thought I would divide my remarks into three groups. The first is just a few remarks about things that strike me as not being deep. And the second is some examples on the general issue of whether depth in mathematics might have something to do with depth or relevance to physics. And the third was to give you one example of something in mathematics that I personally find interesting and deep. So let me start with things that are not deep. I noticed that in the talk so far we hear very few examples of results that are not deep in mathematics, and I think I can understand why. Because it's not, if you try to think, what have I heard lately that isn't deep? I mean, there's just a lot of non-deep things floating around. It's like giving some examples of bad television programs. So, it's my sense that there's at least one kind of theme that for me corresponds to things that I don't feel a sense of depth in mathematics. And it's things that have the following character. There's something that lives in mathematics land, something that is up here that I think of as part of mathematics in the world, and there's something else that I think of as part of people, what people like or what people feel or how people believe, and it's theorems that relate the things up here to the things down here. That's a class of results in mathematics that I'm not enthusiastic about. So let me give you a few examples of results that have this general character. One is that given any continuous function on the interval 0, 1, and given any epsilon, then there exists a polynomial that's within epsilon of that continuous function. So the problem that I have with that is that continuous functions I like, because in the world you see functions and they're continuous. But polynomials, it seems to me, are all about people. It's just that we learned how to multiply x by x, and how to add x and x squared. And so my sense of that theorem is it's relating something about the world to something about people, and therefore it's not something that I find very attractive. Another, I'll be more positive in a while, but let me be non-positive for a moment. A second example is the theorem that every Hilbert space has a basis. I understand Hilbert spaces and that they're potentially interesting mathematically and they're interesting in physics, but having bases, it seems to me, is all about what people are like, because we all learn how to do things with bases, we all love bases, we do calculation with bases. It's a result that relates the mathematics to the people. The third class of results is, well, before I tried to get this to talking with David and Jim, to say any result that has the word classify in it. But maybe that's pushing it a little bit. But I must say that my general sense is that on the whole, nature doesn't classify things and mathematics doesn't classify things. It's only people that classify things. So just to give an example, we have a classification of all connected, simply connected, three-dimensional Lie groups. And the classification is based on that we know that every connected, simply connected Lie group that comes from a unique Lie algebra. And it's easy to classify the three-dimensional Lie algebras. There's like 9 classes or something. And therefore, we end up with 9 classes of connected, simply connected Lie groups. Well, somehow, I can understand that nature might like having simply connected Lie groups, but whether there's 9 or 1 million or whether we have no control at all over it seems to me is mostly about making people feel comfortable with Lie groups. So that's a third example of something that for me lacks enthusiasm. Okay, so the second collection of remarks I want to make has to do with results and their relationship with physics. Well, I'm not sure quite what the relevance of this is to the question of whether a result in mathematics is itself deep, but I think we all agree that physics has something to do with mathematics, and therefore results that are important at some level in physics, it seems to me, are arguably important in mathematics. At least it's worth examining results that have this character. And I want to give you 4 examples of theorems that regarded as theorems in straight mathematics would probably be regarded as of rather little interest and having rather little depth. But when seen from the light of physics, look like they really have a lot going for them. So I do this not because I want to claim that these should get into the realm of deep results in mathematics, but rather just to raise the issue of whether relationship with physics might have something to do with depth of results in mathematics. So the first of these results is the following. There's a class of partial differential equations called the symmetric hyperbolic systems, and they involve fields on a manifold and systems of equations that are first order. They involve the first derivative of fields with some coefficient out here, which possibly depends on the fields, equal to something which is algebraic in the fields. It's a class of equations that have this character. And if these coefficients here have a certain algebraic character about them, then this system of equations is said to be symmetric hyperbolic. Roughly speaking, this set of coefficients has to have a kind of positive definite character. And there's a theorem in mathematics that says basically every symmetric hyperbolic system of partial differential equations has an initial value formulation. That is to say, given a system of equations, these are fields on some manifold, given a system of equations having this character, and given a suitable surface in the manifold of codimension 1, if you specify on that surface the field's phi, then there's one and only one solution of this system of equations in a certain neighborhood of that initial surface, manifesting those initial values on that initial surface. So this is one of the theorems in the subject of partial differential equations. It says that here's a class of equations that have an initial value formulation. Well, in and of itself, I at least haven't heard this theorem mentioned among the list of deep theorems. One might not think of this as having any particular depth in mathematics. But I think from the point of view of physics, it does for the following reason. In general relativity, it turns out, essentially, every system that we ever consider in general relativity can be written in symmetric hyperbolic form. That includes Einstein's equation, the equation for perfect fluids, the Maxwell fields, the Klein-Gordon field, the Dirac field, even suitably written equations for dissipative fluids can all be written in this first-order symmetric hyperbolic form. And furthermore, there are theorems about manipulations of symmetric hyperbolic systems that basically give you rules for how you can combine several symmetric hyperbolic systems to get new ones. And those rules, in fact, are somehow respected by nature in the manner in which various physical systems, electromagnetic fields and fluids and so on, are combined. So, for example, the act of combining an electromagnetic field and a fluid to produce a charged fluid reflects a theorem about how to combine symmetric hyperbolic systems. So here's an example of a theorem. All symmetric hyperbolic systems of partial differential equations have, in this sense, an initial value formulation, whose interest, arguably, which is arguably deep by virtue of its relation to physics. So that's the first of these 4 examples. The second example is the irreducible representations of the Lie group SL2C. So SL2C is the spinor group, and we know all irreducible representations of SL2C. They correspond, roughly speaking, there's a scalar representation, and then there's they're characterized by their spin. So there's the scalar, the spin 0 representation, the spin 1/2 representation, the spin 1 representation, the spin 3/2, and so on. The discovery of all the irreducible representations of SL2C, I don't think would qualify in its own right as a deep result in mathematics. On the other hand, we look around us in the world and we see these particles, and we discover that these particles have spin 0, 1/2, 1, 3/2, and so on, and that they correspond exactly to the irreducible representations of this group. And we furthermore believe that this group relates to the physics that describes these particles, so that this result about representation, it's an easy result about representations of this group, then acquires a certain level of depth by virtue of its relation to physics.
Didn't Hermann Weiss say that an elementary particle actually is an irreducible representation of this group?
Yeah, and I think that's a fair. I mean, I feel comfortable with that because I don't think particles are groups, but it is accurately described by the representation of the group. I think we could find wording that would withstand that our lawyers could work something out. The third example of a result is a proof of what's called the positive mass conjecture in general relativity. This was a long-standing conjecture. I don't know how long, but how long was it? 20? Was it around for 20 years? Yeah. So the question was the following: that general relativity is a system of equations that purport to describe the gravitational effects of a massive object. And we all know, and the mass density of an object could in principle be positive or negative. That is to say, the mathematics doesn't prevent you from making an object of -5 pounds. On the other hand, suppose that you require that the local mass density of each little bit of the material constituting this body is positive. So you require that the mass density here are non-negative. Non-negative, 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 non-negative. You make an object out of material composed entirely of non-negative mass density. And now you take this object and you go off at infinity and you measure the effective gravitational mass of that object, e.g. by dropping a small rock and seeing if it falls that way or that way. So in Newtonian gravity, it's obvious that if the little bits of matter are all a positive mass, then the total effective mass measured asymptotically will itself be positive, because the force on the small rock that you drop is the sum of the forces on all the little pieces, and when you add them all up, it falls this way. In general relativity, however, things are not quite so simple because the equations are nonlinear. So we can't write the force on this little rock as a sum of the forces due to the little pieces because of the character of the equations. So it was a long-standing open question in general relativity. Is it true that if you take an isolated object, not necessarily static, just some isolated object, composed of little bits of matter, that each of which is local positive mass density, that the total effective mass of the object measured asymptotically must itself be positive? And that was actually proven. And what's striking about the proof is that, well, first of all, what's striking about the proof is that the proof uses spinors, which have nothing to do with this problem. This isn't a problem about electrons and spin 3/2 particles. This is just ordinary classical tensor fields in general relativity. The proof consists of introducing a spinor field on this space, which satisfies a certain equation that's linked up with the behavior of the material, and this spinor field has a certain asymptotic behavior at infinity, and then proving the existence of solutions of this spinor equation. And once you have existence of solutions of the equation, everything is very simple, because this equation has the property that there's some divergence law that says the divergence of something equals something, a different something, something prime. And when you integrate this, the right-hand side is non-negative by virtue of the positive mass density of the material. You integrate this side by parts, and this surface integral becomes effectively the total mass of the system. But the field that goes into this equation is a spinor field, first of all. It's not an ordinary tensor field, which satisfies some spinor equation. And to extricate the spinors from this argument, well, I think it's fair to say it doesn't look easy, nor does it look interesting to try to do it. So here is a result, this theorem, which, again, taken as pure mathematics, I think would not be on anybody's list. But on the other hand, first of all, it's interesting in physics, and second of all, it's striking because it has this character that we've discussed earlier, that it invokes features that weren't in the original problem. The original problem involved only tensor fields, but this theorem involves a spinor field on the spacetime. So that's the third of the four, and the fourth one is the Cpt theorem. So we formulate axioms for quantum field theory in special relativity. So the axioms say, well, you have these fields and they satisfy various conditions. And as part of the axiom system, there's a requirement that the full Poincare group act on the fields in the system. And the full Poincare group includes both spatial reflections and time reflections. So as part of the axiom system, there's an action of space and time reflections on these fields. And furthermore, we include within that axiom system a condition to the effect that there be a certain operator on these fields that corresponds to a charge reversal operator. So consider this axiom system with its requirement that there effectively be space and time reversal operators on the fields, and additionally with the requirement that's put into the system that there be this charge reversal operator on the fields. Then it's a theorem that says that it follows necessarily that the operator that you get by combining charge conjugation, parity reversal, and time reversal is in fact the identity operator. So this is just a theorem that's computed. It's extracted from the system of axioms. The axioms were not set up to make this happen, but it turns out that it does happen within the axiom system. Again, this is a piece of mathematics, and now the striking thing is that we observe this to be the case in elementary particles. We observe it to be the case that the combination of charge parity and time reversal is the identity and the behavior of particle systems. And this isn't just a talky-talk thing. There are experiments in which this is tested, in which you say, okay, if CPT is true, then this nucleus will emit particles in this particular pattern, and indeed is found to be the case. So here's a fourth example then of a result in mathematics, which I think no one would put it in their top 10 list of deep results in mathematics, which, however, requires at some level a depth when interpreted in terms of physics. So the sort of summary of all this is, I'm not trying to argue that physics is a good criteria or even that it should be included at all in anyone's list of criteria, but I would suggest that physics at least points us in a slightly different direction from the direction in which we might be pointed if we thought purely in terms of mathematics. So that was the second of the three topics. So the third topic that I wanted to talk about was just one example of something which gives me the flavor of feeling depth in mathematics. When I got the original email from Penn on this seminar, what I wrote back and said, here's my prediction. Everybody who you invite to this seminar will immediately accept. And the reason is that everybody thinks that they have a real feeling for what the deep results in mathematics are, and wants to convince everybody else that this really is that their views are really the right views. And maybe I only said that because that was my immediate reaction. So my sense is that hands down there's one result that qualifies the best for this, and that's Girdle's theorem. And that's what I was going to tell you about. But since we've already talked so much about Girdle's theorem, I thought I would tell you, instead of that, I would tell you what my second choice is, which is quite a bit below my first choice, but we only want to hear so much about Girdle, so I'm going to tell you my second choice. So my second choice is things that are related to P equals NP. So what I want to do is I don't want to talk about P equals NP. I want to talk about another class of results that I believe to be closely related to it, which has, I think, a little better of a feel than P equals NP. What I don't like about the things this set of things is that, to me, polynomial dependence is not interesting, and it has all this polynomial stuff in it, which turns me off. So I'm going to tell you a sort of a set of comments that don't have polynomials in them, but have the same idea as P equals NP, and which I think are attractive. Presumably they're all subsets or something, have a sort of attractive candidates for something that represents a kind of depth. And the depth occurs, it seems to me, on two levels, just to anticipate. One level is that these aren't theorems, first of all. These are just statements, is that when we look at the statements, we just don't have a clue as to how to prove them. So usually you see a statement, you say, well, yeah, I guess I'll integrate by parts and then put this over on the other side and then invoke the somebody other's theorem. But these results, at least my reaction is I read them and I just have no idea how to begin on getting a proof. So maybe, I'm not sure that's indicative of depth, but it's indicative of confusion, I guess. And the second thing is that these results have other implications outside the results. So my plan is to tell you about these things. So we start by fixing any old computer language. So whichever one you happen to like, if you like C or Fortran or one that you made up last night or anything else, use your favorite computer language. And we're going to consider programs, generally, that have the following character. They begin by inputting a string, some string of characters, and then the program does things, so it works. Does chugga, 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 and then one of two things happens. It might run on forever, or it might, depending, output some string. There might be some output. So we're going to consider programs that have that character, and for whenever there is an output string, there'll be some number of steps that the program must undergo in order to produce the output. And that'll be some function of the input string. So the number of steps will be some function of whatever the input string is. So this function then represents how many steps the program takes to get the answer. I might just insert a remark here that you might say, wait a minute, I should say the number of steps is only meaningful up to a factor. So if you take this function, the number of steps it requires to get the answer, and multiply it by 10, that's regarded as the same difficulty of the program. And the reason is that things like factors of 10 can be achieved by buying a more expensive chip or by everyday practical things. So in order to eliminate the issue about who has the most money to spend on chips, we regard functions that are bounded by multiples of each other as equivalent functions. So you might now say, wait a minute, I'm already a little bit unhappy here because it looks as though this difficulty function, the function that gives you how many steps it's required to get the output string, you might say, might well depend on what computer language that you choose. So if you choose Fortran, you might have one difficulty function. If you choose C, you might have another. And how do I know that the two are equivalent in this multiple sense? this is a sort of a church's thesis for difficulty, because it's supposed to say there's a universal notion. So if you take C and Fortran, it's not hard to prove that the two are equivalent. Or if you take any other language that people use, it's not hard to prove. But I guess there's a kind of church's thesis here which says that for all reasonable computer languages, this function is universal. It depends only on what the program is and not the language in which that program is written. In any case, then, let's consider this arrangement. And now let's consider a program that has the following character. The input of the program is two integers, n and k, where k is less than or equal to n. So these are both positive integers. And let us, just to simplify matters, let us suppose that the program always halts for any k less than or equal to n, and the output is always either yes or no. So this is a program, then, that accepts an integer less than n and either says yes or no. And so what we're thinking of fixing n and varying k. So k goes from 1 all the way up to n, and that gives us a collection of yes-no answers. Let us suppose, there's really two, I'm going to give you two versions of this, so here's one of the versions. Let us suppose, just for fun, suppose that for each n, either you get yes for at least 60%, or let's say 80% of the k's, or you get no for 80% of the k's. It doesn't have to be the same for different n, but for each value of n, so you take an n, for each value of n, there's n possible values of k. For each of those values of k, you're going to get an answer that's either yes or no. Let us suppose that it's the case that somebody always gets 80% of the answers and the other one only gets less than 20%, at least 80%, at least. Okay, so here is an example of a okay, so here is a program then that takes as input. This is a sort of an arrangement, and this is an instance of that arrangement. Produces either yes or no, and always gives the yeses either 80% or the no's 80%. And now I want to consider a new problem. The new problem will have as an input an n, a positive integer n. No k for this one. And the output will either be yes or no. And the output has to be yes if 80% of the k's would have given s, and no if 80% of the k's would have given no. In other words, this is the program that takes an n and tells you whether the preponderance of instances for all the possible k's is yes or no. Okay, so this is a problem, and I claim there's a program that computes this problem. What the program does is, given an integer n, it runs the original program for the n instances of the various values of k, compiles the results, find out who gets 80%, and then report the answer. So there certainly is a program that computes this, and we can ask, what will be the difficulty function of this program? Well, the difficulty function of this program will be equal to, doing it this way anyway, it will be equal to, if we look, it'll be equal to the summation over k of f of n and k. Because it has to run that program for each of the k values, actually only 80% of the k values, but anyway, some number of k values, which is equal to k, which is less than or equal to k times the max over, n times the max over k of f of nk. So there's n terms in this sum, so it's less than or equal to n times the maximum value of the function. Okay, so we have a program that given any n, checks k's and gives you yes or no 80% of the time. And we consider the problem, we ask the question, which is the preponderance of the answers, yes or no? And there certainly is a program that will compute it, and it has this difficulty. Okay, so now let me tell you an assertion. Assertion. There exists a program which computes this problem with difficulty in other words, you can find out what the preponderance of k's is in a number of steps, which is not the number of steps it takes to check every possible k value, but rather a number of steps that it only takes to check one k value. Okay? On its face, this is an absurdly strong statement. So let me give you an example of how strong it is. Suppose we want to take the question of whether whether there's a proof of an assertion in piano arithmetic. Well, we can formulate that as where we consider the k. Suppose we have an assertion in piano arithmetic, and we want to know if there's a proof of that assertion in less than 10 to the 12th, in a number of steps less than 10 to the 12th. Then we can let n be big enough so that it tries every possible proof. And we want to know, I'm sorry. I cancel that example. That is an example for the second of the two, not for this one. So let me just leave it at this point. Okay. So the statement is that you can find you can find a program that will find the predominance in a way much faster than it would be to check everything. That's what the statement is. And so here's an assertion, and I have no idea how to prove it or how to find a counterexample. So you might think, well, the idea is that it's easy to think of programs that have this property that give you yes or no. The problem is that if you have a program that gives you yes or no, typically around half of the k's will be yeses and half or no. So you have to bias the program in just the right way that for at least 80% of the k's is yes or 80% of the k's is no. So you have to get rid of the instances where about half of them are yes and half of them are no. How do you get rid of the ones that are about 50-50 and leave only the 80% or better guys without doing it in a method that already can figure out which one is going to be the winner? How do you make it so that somebody will win in a way such that you don't know ahead of time who's going to win? That would be the way to try to prove this, but I just have no inkling how to prove it. So let me give you an implication of this statement. Okay. The implication is the following.
Whose theorem is this?
Pardon?
Whose theorem is this?
Oh, you mean this assertion?
Yeah.
Mine. The 80% doesn't make any difference. You can easily prove this is true for 80% if and only if it's true for 60%.
Is this a true assertion or not?
What?
Is this a true assertion?
No, this is just an assertion. I have no idea whether it's true or false. It's not a theorem. No idea. What I know is that if you just imagine trying to prove it, it's just very difficult because it's very hard to set things up. So you might say that it's very hard to set things up so there's a predominance of either yeses or nos. It's hard to do that in a way such that you can't figure out who's going to win. You've got to make sure that somebody wins without having it easy to figure out who wins. And it's very hard to set things. I shouldn't really say, I think this is essentially a P equals NP kind of question. P equals NP roughly says, if it's easy to check, it's easy to find. Okay. Well, this has the same character. It says, if somebody predominates, then it's easy to figure out who is doing the predominating. Okay, so let me give you an implication, just as an example, an implication of this. So I'm giving this as an example of an assertion which arguably might be regarded as deep in mathematics, because one's reaction is I have no idea what to do. But I want to give you also an example of an implication of this assertion. So let's consider the following set of rules. We're going to invent a new computer language which has, in addition to the standard steps in ordinary computer language, a probabilistic step. So we add a new step which says randomly choose either a 0 or a 1 and insert it in a location. So we have a new step now. Select 0 or 1 randomly and put it in a given location. So we can now write programs that have this random selection, this probabilistic character, and we could have programs that chug along, maybe using the few probability steps in the program, and then give some answer. And we can say that such a program solves a problem if it gives the right answer 80% of the time. So we have a new notion of computability, namely computability with probability. And we have a new notion of solvable, namely it only has to get the right answer 80% of the time. And now we can ask the question, is this new notion of computability with a random number generator, the same as computability as ordinary computability? Well, it's the same as ordinary computability if and only if this assertion is true. This assertion is a thinly disguised statement that probabilistic programs will do no better than non-probabilistic programs. As far as I know, it's completely open whether there's some whether in principle you could have new fast computational methods that use probability in this essential way. Okay, so that was one example. Now let me give you a second example. The second example is the following. Again, we have a program, has a number of steps. There's an n, there's a k, and it gives any yes or no. But now we want to write a new program that has the following property. We want to write a new program, which again will take an integer n and will return yes if the original program gives yes for any k, and it returns no if the original program gives no for all k. So the new program takes an n and asks whether the original one will ever give a yes. If it's always no, it reports no. If there's any one for which it gives a yes, it reports yes. So this is the sort of find the needle in the haystack, that kind of program. So again, we could write a program that does this computation. And again, that program, which would simply check for all values of k, looking for a yes, would have this difficulty function. Now consider the statement that there exists a program that will do this with the same thing, with difficulty function max over k of f of nk. So this says it's easy to find out whether there's one or not among all the possible k values that produce a yes for you. So here's another statement. So now this is the one I was thinking of before. So let me give you an example of an implication of this statement. Suppose you take an assertion and you want to know whether there's a proof of that assertion, say in piano arithmetic, of less than 10,000 steps. Then you write down the program that checks all 10,000, all possible proofs that involve 10,000 steps. That's a lot of k's, and which checks to find out if it is a proof. So that's a program that has to examine an enormous number of k's and check whether any of them are a proof. If it is, it gives a yes. If it isn't, it gives a no. So this new program will tell you whether it says yes or not in this many steps. So it says, this new program says, the problem of deciding whether an assertion is provable in piano arithmetic, say, in n steps, is no harder than the problem of checking whether an n-step proof is a proof of piano arithmetic. which is pretty easy to do. In other words, if this statement were true, it would imply, among other things, that you can check you can't. It doesn't mean that you can find out whether assertion is provable in piano arithmetic, but it does mean that you can find out very easily, in terms of the length of that of the proofs that you're looking for, whether there is a proof in piano arithmetic up to a certain number of steps. So if this were true, for example, then if you take some open question in mathematics, you would be able to easily decide whether there's a 10 to the 7th step proof of that theorem by simply running this corresponding program. And this has the same, also, for example, you would be able, it's easy to show that you could decide whether an integer you could find the prime factors of an integer in a number of steps that's effectively the number of digits in the interval, that's proportional to the number of digits in the integer, which we're, of course, not even close to being able to do, though we can't, as far as I know, prove that we can't do it. So if this statement were true, then it would mean that, the problem of finding proofs of things would be faster, and breaking computer codes would be relatively easy. And again, I have no idea how you would prove something like that. At least when I think about it, I can't think of even a beginning line to try to prove it, or a beginning line to try not to prove it. Well, this is sort of the tip of the iceberg of this general theme, which is, if it's easy to check, it's easy to find. But and what seems to me is striking about this set of lines is that that it just looks so difficult to get anywhere on them, and these kinds of results would have implications that go outside of the results. So this would be my candidate for the second deepest things, in my opinion, in mathematics. Thank you.
The example you've given does sound very much like P equals NP.
Yeah, right.
You could take propositional logic, the satisfiability problem, for instance, deciding satisfiability instead of checking all instances, you only have to check one.
Yeah, it's not that you only have to check one, it's that this is a very diabolically clever program, which then has a number of steps that's the same as the number of steps of checking one. Right, but this isn't a program that checks one. Nobody's saying that the program that does this is the one that just picks one and checks it. Right. So if you're doing some specific problem, like is there a proof in piano arithmetic, this would be some deep, clever program. Right. Nobody has a clue how to write that program. Yeah, that's right.
Program behaves as different.
Yeah, that's right. Yeah, difficulty-wise, that's basically, yeah, right.
Yeah, just a historical remark. The second problem that you bring up there is essentially the one that Girdle has in his letter to von Neumann.
Right.
Right.
Yes, that's right.
Which I think is, if you generalize what Girdle says, it's essentially equivalent to P equals NP.
Well, people say that, but I have.
Well,
this is sort of like it, but there's no polynomials here, right? There's no varies like n squared or anything here.
Yeah. Okay. So what is the problem if you're not stating it in terms of polynomial time?
I never use the word polynomial. I never use the word polynomial.
Right.
So it's given a program that, given these two objects, says either yes or no. And we want to write a new program that, only given n, will say yes or no depending on whether all the k's have this property. And we want to do so we want the program to run in this number of steps. So the word polynomial never appears, which, from my prejudice, which I don't expect others to share, is an advantage, since I think of polynomials as being about people, and this is supposed to be about mathematics.
I see. So you're giving a slightly different version of Gödel's
Well, yeah, I suppose you could think of it that way. Yeah, that's right. Yeah, because I never liked the n in there. Yeah.
I see. Okay. I understand. Yes,
Yeah.
You're asking.
I doubt that it's.
Thank you.
I mean, I don't think it's substantially different. I mean, it's just
I don't know. I have to.
yeah, just sort of
Thank you.
emotionally different.
Good.
Could I just ask one question about your very first example, which was about the density of the polynomials inside of the space of continuous functions?
Yeah.
I mean, you mentioned that one of the reasons that didn't count as deep in your book was polynomial seems like you're concerned with human interests and human capabilities. But another consequence of that result is just that you can view the space of continuous functions as a very sort of natural polar space that is separable within the tricycle space, and you can apply all the results of the stricter set theory to it. So you know it's Borel isomorphic, for example, to all of the other incredible polar spaces. I mean, so that result might have a lot of consequences, which might themselves be counted as deep. And so, I was wondering, does your concern about the non-depth of the result itself can extend to many of its canonical consequences?
It's hard for me to answer that in generality, but let me try to answer it in specific, whatever the opposite of generality is. That if you give me an example of something that doesn't involve the polynomials that you find interesting, like, oh, then it's separable. My immediate reaction is I'm going to try to find a direct proof that doesn't go back through the polynomials. Just as if you give me, there are many things in Hilbert spaces that people prove using bases, where if you try to get a proof without basis, it's easier and clearer and simpler. So my hope would be, but if you found a sequence of results that for which you really seem to need the polynomials, that I can't, then I'm only going to tell. I don't know really what's deep. I'm just telling you my reaction. My reaction would be, first I'd try desperately to get the polynomials out of there, right? And if I absolutely ended up, then I would try to see if I could, then it would seem to me that there's actual mathematics in the polynomials, not just people. And then I would try to see if I could figure out what is the mathematics that underlies the polynomials so that I could love the original theorem. Okay, but
I'm just intrigued by your dislike of polynomials. Can we trace it further back? Do you dislike addition and multiplication too?
No. I have to be careful, yes. But okay, right. I don't dislike addition and multiplication, but I dislike x. So that's intended as a challenge, right?
I'll have to work on that.
Well, I'm not sure that, it's like everyone's prejudices. It's a little hard to figure out where they came from. I think my sort of sense is that I think of 0, 1 as being a one manifold, and x is a coordinate on the one manifold. And coordinates generally, it seems to me, confuse matters because nature doesn't put coordinates on things. So since polynomials involve this coordinate on the manifold, I tend to shy away from it. But I don't want to make this a religion. I mean, that you could maybe convince me that especially, if this program of producing a sequence of results, which seem to be of interest, and which I'll even start to concede, even if I can find other proofs, if the proofs with polynomials are very direct and simple, then I might come around.
Well, one of after hearing about polynomials and this NP problem, I want to tell a little anecdote.
Okay.
So the ICM talk in Berlin in 1998, Mike Friedman actually gave a talk about this NP problem. And he introduced polynomials, and he said, well, so what is a polynomial? What's the most elementary fact about polynomials that we know? And he said, well, the most elementary fact about polynomials is Gromov's theorem that the group of polynomial growth is virtually nilpotent.
Well, something you said about when you mentioned coordinates, there's when you think about when you're thinking about things being manifolds and so forth, does the fact that these are visualizable when they can admit, you know, that you can draw pictures of them, is that something that matters to you, or are you just sort of saying no?
I like to draw the pictures, yeah.
Yeah, but do you take that to be sort of essential to what counts as, say, you describe it doing in geometric?
I can see that. I mean, it's hard for me to close this box since I'm the one that opened it up. Well,
here's why
yeah.
I'm asking. Like, there's a book by Lange called The Geometric Algebra, in which he actually says things that sound a lot like what you were saying about bases. So he talks about linear transformations versus matrices, but very similar ideas are being articulated. And the thing that's striking about this is he clearly announces that he's going to carry out a geometrical approach to linear algebra, and he works very hard to do this. It's a fabulous book in many ways. The thing that's striking about it is that there are hardly any pictures in it. Right? There are maybe 2 or 3, and they all are illustrating very trivial things. And so you're left with the sense, well, if that's what counts as geometrical, then we've got a very abstract sense of what counts as geometrical here. It's sort of given by sort of maybe not having coordinates, maybe the being independent, or maybe being invariant under certain kinds of permutations and so on. And the fact that you can draw pictures of it is kind of an accidental fact that may be useful for certain pedagogical and orienting reasons, but it's kind of secondary. And I was wondering if that was something close to your sense of why it is that you think bases are kind of distractions, right? Not necessarily because geometry has anything to do with visualizability or anything like that, but because there are these sort of fundamental mathematical facts underlying what counts as geometry.
I hope that it's only a coincidence that this person on the one hand didn't want to have bases and on the other didn't want to have figures. I don't see the two related. Certainly if you draw pictures of vector spaces and you show how to add vectors and you show you want to prove that given a subspace of codimension 1 there exists a vector that's perpendicular to it, I would be all for drawing pictures, but what I would feel less comfortable with would be saying choosing a basis where the first n-1 vectors are in the plane and then doing algebra.
It was kind of a diagnostic question because I was wondering if something similar could be true of your understanding of the situation in Arden's, but I think you're coming at it in different ways.
I think my dislike of bases is that my feeling is that the reason people like to do bases is because they learn to do algebra at a very young age, and so everybody wants to convert everything back to algebra instead of just staying with geometry, where once you get into the flow of it, it's actually much easier than trying to convert it to algebra.
Well, you can push this remark even further. It's not only
Great.
bases are overrated, and I completely agree with you, it's also coordinates.
Oh yeah.
Oh God.
Yeah, right.
In geometry, they start, with their coordinates and the indices. That's
Right.
the wrong
And
approach.
when people do partial differential equations, they make it would be so simple. Many times things are made like a factor of 4 more complicated by just getting things straightened out that you don't even need to straighten out because you never had to introduce them. It always feels like to me as though it's only because we learn these things. Everybody learned functions, and somehow if we could only make everything be a function, it would be, and instead of having to deal with a vector, if we could only deal with its components, then we could do something that I learned in 5th grade. Yeah, that's my reaction. But
yes, I think this is, at least in my field, the standard point of view is if you have to choose bases, if you have to choose coordinates, it's ugly, you're doing it the wrong way, you're not going to be able to generalize, and it's definitely not, the proof from the book does not.
never, right? Yeah, right. That's right. But I was mentioning this not so much to try to force everybody to my view, but in order to generate some examples of things that might qualify potentially as deep results in mathematics that don't give me that feeling, which is things where you reformulate something which nature didn't or mathematics didn't want to have in that other form into a form that you're comfortable with. Yeah.
So your talk had an interesting relation to one of the 4 questions that Penn posed for the conference, and that I remember it's the 4th asks whether our judgments of depth in mathematics are somehow tied to our interests. And so it was sort of posed as an open question. It's interesting in your talk that you seem to start from the idea that if our positive judgment about something in mathematics is tied back to our interest, that automatically disqualifies it from being deep. But it seems that you're presupposing the answer to Penn's 4th question is no. This is an objection. I'm just wondering if you have something more to say about that.
I think the problem is I don't think I really have much to say about something being deep independently. I mean, when I got the notice about the meeting, I sat around and thought, okay, what do I think is deep? And I just couldn't really focus on that somehow. I could think about what I think is interesting, but I couldn't distinguish between thinking it's interesting and thinking that it's deep. So I think it's probably maybe a lack of practice in thinking in these terms or something. So I didn't mean to suggest that interest is the same as deep or that my interests have anything to do with depth, only that I don't know any other terms to think in terms of. So these examples I gave of things that I didn't find interesting, I mean, my sense is that if we knew what depth, if I knew what deep meant, they wouldn't be found to be deep either, but I don't want to push that point. It just doesn't strike, it's not mathematics that sounds like much fun to me. Whereas this mathematics feels like it's fun.
Yeah, I mean, so I just want, so 2 very quick things sort of connect up what you said to some things that were said this morning. One is that, I don't remember now who said, maybe it was Marc, but there are sort of 2 different ideas. One was there was kind of backward-looking idea that John Stillwell had about depth in terms of what turned out to be difficult and required lots of resources that we didn't expect. Jamie had a forward-looking notion of depth in terms of what would become fruitful. And what you're describing at the end of your talk, the 2 examples related to people's NP, seems to lie somewhere right in between, in the sense that here are some things that seem really, really hard. Of course, it might turn out that they aren't hard.
Right.
We don't know how to do it.
Right.
Once we do know how to do it, it'll turn out it was easy.
Yeah.
But which we have some reason to think would be fruitful. And this makes me wonder if there are maybe there's more commonality between, this is not really a question, just a thought. Well, maybe there's more to be found in relation to these 2 different perspectives that at one point were suggested were diametrically opposed.
I see.
Than originally thought. The other thing is that both you and I think to some extent John suggested that something that I think is deep. And so one of your big examples was the classification of simple Lie groups. And John, you said that the classification of finite simple groups was deep. But the classification of simple Lie groups, well, Killing did that 10 years after Lie introduced Lie groups, and that wasn't such a big deal.
Oh no, I didn't mean to say that. That was a really big step forward. It just didn't take very long.
I see. So I actually wanted to ask you: do you think that the fact that it didn't take long doesn't means that it's? I mean, it could be a big step forward without being deep, I suppose.
It was perhaps a fluke that he managed to do it.
So
there has been an article written on Killing's paper which described it as the greatest mathematical paper of all time. So some people admire that very.
I always thought that you made some mistakes in this classification.
Yes, I think Cartan fixed it up in his thesis a couple of years later.
So I like whoever wrote that paper. But it doesn't even have to be correct. I mean, it seems to me that that there are two ways of understanding that kind of thing. One way of understanding it is, it turns out that there are these four kinds of simple Lie groups, and then 5 or 6 others, individual cases. Another way of understanding it is that it turns out that if you take these two quite different areas of mathematics, group theory and differential geometry, you try to put them together. It turns out that there are sort of deep constraints that arise that mean you can only do it in certain ways, and that we can say something systematic about what those ways are. And it turns out that in order to say something systematic about what those ways are, we need to appeal to yet another area of mathematics. And it turns out that all of the information about what those ways are is fully encoded information about the tangent space, the identity of these manifolds, the Lie algebra. And that seems to me to be an example of the sort of thing that, first of all, is a big result. It pulls from lots of different areas. It's unexpected, and so just dismissing that as well. That's just really about what we care about.
Well, which part was the part that only we care about? I mean,
well,
getting the Lie algebras from the Lie group and the Lie group from the Lie algebra. I'm not saying that's something only we care about.
But that's what the classification result is.
Well, this is like the discussion we had before, where my reaction is always we start with a little classification over here, but then you take everything that's sort of interesting within 100 yards and toss it in and say, oh, that's part of the classification, so that I can in the end say, I don't find the classification interesting because you're forcing me to say, I think the relationship between Lie algebras and Lie groups I find interesting. And if that leads to some classification result, so be it. And if I don't want to buy the classification result as interesting, I don't think I have to reject. I'm not sure how this would play out. In the end, I will probably be defeated in this. But that'll be my initial position. Is that I don't think I want to say that every possible classification thing is something wrong with it. But I'm just trying. My general sense is that a lot of, basically, what constitutes a classification? As we discussed, have 4 manifolds been classified? Sure. Consider the collection of all 4 manifolds. So when one says, I don't like that, and I say the question is why, right? And then the final classification means that that's something you do like. So classifications generally seem to me to be about liking things. On the other hand, classifying the representations of SL2C, it's not us that's doing the liking, it's nature. And so I tend to be more favorable. There was one remark I think I should also make. If this is true, if this statement is true, you can also prove that some large class, some moderate class of problems for which it's claimed that quantum mechanics will do the calculation more quickly than classical mechanics. In fact, quantum mechanics will not do it more. You could use this statement to show that for some class of problems, quantum mechanics will not give you any advantage, even though it's widely believed that it would. So this would also, there's another area where this question would peek its head out. That's true, and pretty uncomfortable.